Okay, so now we are recording. And recall last week we were looking at this example from section 8.7 where we wanted to find the power series for this function e to the 2x power times the natural log of 1 plus x squared. And of course, we could use the definition of a Taylor series or a Maclaurin series and repeatedly find derivatives of this function and then work it that way to get the Maclaurin series. But the problem is the derivatives of this function are going to get fairly complicated. They're going to grow in size because it's the derivative of a product, and then when you take the derivative of a product, you're going to get the sum of two products here, and you got to take them to get the second derivative, the derivative of those two products, and it gets kind of messy. So what we can do is, well, we recognize that section 8.7 has a table. It's table 1 in section 8.7. It's a table of Maclaurin series. Now, this table, I have reproduced it. Well, I've actually made it a little more, it's not exactly reproduced, but almost. I mean, what I've done is for the Maclaurin series in table 1 from section 8.7, I've rewritten most of those functions down with their Maclaurin series. And then I've included intervals of convergence. So the textbook will show radius of convergence for every Maclaurin series, but I think the interval convergence is better to have, because if you know the interval of convergence, you can get the radius of convergence. So hold on here. Let me just get this off here. Okay. So what we do is to find the Maclaurin series for e to the 2x power, we look at the Maclaurin series for e to the x power. And to get the Maclaurin series for e to the 2x power, all we need to do is substitute in 2x for x. And so when we do that, that's what I do here. I wrote down the Maclaurin series for e to the x power. And incidentally, that table here, this table, well, this handout that I have, that handout is located under the course content folder in Blackboard for section 8.7. There you can click on a link there and download that handout. And you will have that handout available to you on the final exam as well. It will be one of the supporting documents that you can download in examining. So, okay, e to the 2x power, we have the Maclaurin series, and now based on that, I can get the Maclaurin series for, so yeah, the Maclaurin series for e to the x power, I have it written down. So the Maclaurin series for e to the 2x power, I can write down the terms of that Maclaurin series. And so turns out that e to the 2x power, if we write out some terms, that's going to be 1 plus 2x plus 2x squared plus 8 over 6 x cubed, and so forth. Now we can do the same thing for the natural log of 1 plus x squared. Are there any questions on this Maclaurin series for e to the 2x power? Any questions on that? Okay. Well, let's get the Maclaurin series for the log, the natural log of 1 plus x squared. So if I go to the table, okay, I have the Maclaurin series for the natural log of 1 plus x. There it is. So let me go to the whiteboard. We go to the whiteboard here. And this is really review. Okay, this is really review, because we did this last week. But the So the natural log of 1 plus x, its Maclaurin series, okay, starts at n equals 1. And let's see. This is that Maclaurin series. So if I want the Maclaurin series for the natural log of 1 plus x squared, I'll just substitute in x squared for x. So this is called creating a Maclaurin series from another Maclaurin series. Okay, that would be the Maclaurin series for the natural log of 1 plus x squared. And if we write out some terms of this are going to be, well, the first 3 terms are going to be x squared minus x to the 4th over 2 plus x to the 6th over 3. It's an alternating series. And okay, just so you see, okay, how do we get x to the 6th over 3? X to the 6th over 3. Well, if we take, hold on here, let me just check one thing. Hold on. Right. If we take n equals 3, that's the third term. N starts at 1, so n equals 3 would be the third term. So negative 1 to the 3 minus 1 power times x to the 2 to the times 3 power. All divided by 3. And that'll get you negative 1 squared times x to the 6th over 3. Okay, and so that's how you enumerate the terms. What we're going to do now is the following. We're going to take this series here, this Maclaurin series. We're going to take that Maclaurin series and we're going to multiply it by the other Maclaurin series that we found. The other Maclaurin series that we found, you see here, it should be here. Is the Maclaurin series for e to the 2x power. Now remember, they tell us we only want the first 3 non-zero terms. First 3 non-zero terms in the Maclaurin series. So, okay, let me show you how do we do this then. So what I've done is, hold on here, let me just change the font, this pen. Okay, so we are multiplying e to the 2x times the natural log of 1 plus x squared. So here's the Maclaurin series for e to the 2x. And here is the Maclaurin series for the log of 1 plus x squared. What I do before I do the multiplication is I just do a little simplifying of both of those Maclaurin series. And then I'm going to start to do multiply. But let me let you get down to here. Let me know if you have any questions. Okay, and then let me give you a moment to catch up. Okay, so okay, how do we multiply this? How do we multiply this? Let me get my email off here. So we want the first three non-zero terms. The first three non-zero terms. So, yes, Clay, a question?
So, Professor, my question is on the first line that you have circle one blue and one red. How are they connected? Like, is this line going to that line, or?
Well, so what I do is this. So I look at the one here. Let me just clear this here. I'm going to take the one and I'm going to multiply it by x squared. And that's how I get 1 times x squared. I'm going to take the 1 and I'm going to multiply it by the negative x to the 4th over 2. That's how I get 1 times negative x to the 4th over 2. Now, I'm thinking the first three non-zero terms, maybe I won't be getting to the 6th power. So what I'm doing is I'm selectively multiplying things. I mean, I know if I were to multiply the terms together, I'd have to multiply the 1 by all of these terms, by all of those terms down there. But I only want the first three non-zero terms of the Maclaurin series. So I'm only going to do these two multiplications using the 1. But the next term in the top series is the 2. Yeah, that's right, Yonatan. It's like you're taking the smallest term from the 1 series and multiplying the other series. So now the 2x, I'm going to take the 2x and multiply it by x squared. I'm going to take the 2x and I'm not going to take the 2x and multiply by negative x to the 4th over 2, because that would give me a term that's of the 5th power, and I might not be including that powers of the terms of 5th degree. So 2x times x squared gets me this. Okay, so notice I have plus dot dot dot. That means there's more terms, but those terms are of higher degree. Finally, I'm going to look at this 2x squared. 2x squared, I'm going to multiply it by this x squared. 2x squared times x squared. You see, and you see, that will ensure, like, all of the terms, all of the remaining terms, and they're an infinite number, all of the remaining terms here are, and all of the remaining terms here, let me just double check it. Yeah, all of the remaining terms here, and all of the remaining terms here. These terms are of, these terms are higher than fourth degree. But you see, I have a second degree, a third degree, and a fourth degree term. So that will give me the first three non-zero terms. The x squared here, 1 times x squared, that's x squared. That takes care of that. One times negative x to the fourth. Let me just, okay, this is all in the recording, but let me clear this here. So 1 times x squared is x squared. 1 times negative x to the fourth over 2, and 2x times x squared. 2x times x squared is 2x to the fourth. And this here, 1 times negative x to the fourth over 2 is negative x to the fourth over 2. If I add 2x to the fourth, and negative 1/4, negative 1/2 x to the fourth power, that's going to get me 3/2 x to the fourth. And then finally, I got the 2x times x squared. That gets me 2x cubed. You see, and that's all I need. I mean, in WebAssign, I would type this term, I would type those three terms, and that would be it. But that's how you multiply two terms of a Maclaurin series, or that's how you multiply two Maclaurin series. Obviously, if we were to try to get a formula for the product of those two Maclaurin series, that would basically be beyond the scope of this course. But we could certainly multiply two Maclaurin series together and try to figure out what the first, 2 or 3 or 4 non-zero terms are. Or we could divide two Maclaurin series together and figure out the first 2 or 3 non-zero terms. So if you look like in example 13 in the textbook, they do that kind of thing. They do that. So example 13 is another good example that you can look at. Hold on here. There was a question. Oh, Susanna says, how did I get 3/2? So let me see here. Let me show. So are you in agreement that this here is negative 1x to the fourth over 2? And then 2x squared times x squared is 2x to the fourth. If you have negative 1/2 x to the fourth, one moment. Right, you have negative 1/2 x to the fourth plus 2x to the fourth. Okay, that's equal to 3/2, because 2 is equal to 4/2, right? So that's like taking negative 1/2 x to the fourth plus 4/2 x to the fourth, 3/2 x to the fourth. Are there any questions on that? All right, so example 13 in the textbook also is a good example to look at. That'll be very helpful. And let us see here. I want to now if we're good on this, I want to go to another example. So let me just let me get another one here. One moment. Okay, let's do a problem where we have to do an integral. Okay, let me give you a moment to copy this example down, and then we'll talk about the solution. Okay, so this is an interesting problem. Does anybody know offhand the antiderivative of the arctangent of x cubed plus the sine of x cubed? Does anybody offhand know the antiderivative? Is it if it exists, is it one that's easily known or not easily known? Susanna, I don't know if that's right. I'm not saying you're wrong, Susanna, but I'm just saying offhand, I don't know the antiderivatives of those, and likely they probably don't even, like, explicit antiderivatives probably don't exist. I'd have to check your answer out, but for now, let's assume that they don't exist. And so, okay, what are we going to do? We're going to use Maclaurin's series to help us out. Okay, we're going to use Maclaurin's series. So I need a Maclaurin series for the arctangent of x. If I find that, I can get then the Maclaurin series for the arctangent of x cubed. And I need a Maclaurin series for the sine of x. If I can get that, I can get the Maclaurin series for the sine of x cubed. Okay, so we're going to evaluate this. We want this correct to within 5 decimal places. So, okay, here we go. We go down here, and sure enough, in this handout, and remember, this handout is located in Blackboard under the course content link on the course content, I guess, item or folder on the left in the menu. You click on course content, find chapter 8, locate section 8.7, and there will be a link to this. How many have found that? Has anybody gone in? It should be there. But here's the, you can download this handout there under course content, section 8.7 in Blackboard. There's the Maclaurin series for the sine of x and the arctangent of x. So first step is to get the Maclaurin series then for the arctangent of x cubed and the sine of x cubed. Easy enough to do. So, okay, let's go to the next page here. So here is the Maclaurin series for the arctangent of x. And from there, we can get the Maclaurin series for the arctangent of x cubed. let me let you copy that down. Please let me know if you have any questions, okay? Okay, well now for the sine of x cubed, we have the Maclaurin series. Let me put it, circle it in green here for the sine of x. And so the sine of x cubed, we can get its corresponding Maclaurin series. So I think everything is pretty clear, but if you have any questions, please let me know. All right, are we ready to move to the next page? Now that we have we know the Maclaurin series for the arctangent of x cubed and the sine of x cubed. What we want to do, of course, is we want the integral of the sum of those two functions. So, all right, let's go to the next page then. So, okay, here we are. This is the integral that we want to find. And what I'm going to do here is for the arctangent of x cubed, I'm going to substitute in its corresponding power series into the integral. And for the sine of x cubed, I'm going to substitute in its corresponding power series. Notice that for both series, the index starts at n equals 0, the same starting index. And that always makes life easy. You can still add two series if one of them starts at a different index than the other, but you have to make an adjustment to the one of the series so that they both start at the same index. But here we won't have to worry about that. Now, the integral of a sum, well, you have the integral of a sum, right? The integral of a sum here. That then is the sum of the integrals. Okay, let me just lay that out a little bit here. Hold on. Yeah, you have the integral of a sum. That's just the sum of the integrals. Okay, so now you have two different integrals of the sum to deal with. And you've had some experience with this in section 8.6, right? So the integral of a sum is the sum of the integrals. That's the property we're using to get us down to here. For the first series, of course, I mean, for both series, we're integrating with respect to x. That means that -1 to the nth power and 2 times n plus 1 can be treated like the constants because they don't depend on x. And that's why you can factor those out in front of the integral. Similarly, for the other expression, -1 to the nth power and 2n plus 1 factorial, that can also be factored out in front of the integral. And that gets us down here. Some of the most beautiful math, really, that there is, in my view. And then we do the antiderivatives. The antiderivative of x to the 6n plus 3 power is x to the 6n plus 4 over 6n plus 4 power, plus the constant of integration, because this is an indefinite integral. Similarly, well, yeah, you have the same for both, right? That gets us down here. Please let me know if you're uncomfortable with anything, any of the math that you see. Franklin, how are you feeling about the math? Are you comfortable?
Yes, Professor.
Okay, very good. All right. Susanna, how about you? Are you comfortable so far with the math? Good. Okay, very good. Well, what do you think we should do? What do you think we should do ultimately with this summation and this summation? They both start at n equals 0. What can we do with the two summations then, since they both start at n equals 0? That's right, Jonathan. Very good. We can combine those two summations. Okay, and that's what we're going to do. That's what we're going to do. Because we want to get one power series for this integral. We don't want the sum of two power series for the integral. We want one power series for the integral. All right, so if we're good, I'll move on to the next page then. Any questions? Okay. So, all right. Well, what we're going to do then is the two power series here, this power series or Maclaurin series, but I'll just call it a power series. This power series and this power series, since they start at the same index, n equals 0, we can just combine them. We can combine them to get a single power series. And incidentally, the sums of the two constants of integration, C1 and C2, we'll just call C. I can factor out a common denominator here, or a common factor from both terms. X to the 6n plus 4 over 6n plus 4. That factors out of both. And so I can rewrite the power series as you see down here, the very last step. So we are able now to take an indefinite integral and express it as a power series. Absolutely amazing. So we've taken the indefinite integral and we've written it as a power series. And now what we want to do, of course, is compute the definite integral, where our limits go from 0 to 0.2. Now, in order to use this power series to do this, the interval of convergence would have to contain from x values from 0 to 0.2, which it does. Okay. So generally, of course, like you learned, like you've learned that like if you have a power series and an interval of convergence and you take the derivative of the power series, the interval of convergence could alter a little bit, like at the endpoints, but the body of the interval of convergence typically remains the same. It's the same for integrals. So these two integrals, well, I want to be a little careful how I phrase it, but just take my word for it. The interval of convergence will work here for finding this definite integral. So let's go to the next page. Okay, and now we are ready to do our definite integral to compute it. So the limits go from 0 to 0.2, and all right, well, here's the integral written as a power series. I'll just actually, yeah. And I got to substitute in a 0.2 and a 0. Notice that because we have a -1 to the nth power, okay, we have that as part of our power series, that this is an alternating power series. It's an alternating power series. And so we can use the alternating series estimation theorem to help us tell when we can stop, when we have enough terms to get the level of accuracy which is what we want. And that's correct to within 5 decimal places. So I put in x equals, so just like any indefinite integral, you're going to put in the top limit first, subtract, and then put in the bottom limit into the antiderivative. In this case, the power series. So here's the 0.2 that gets put in. And then if I put in 0 for x, I put in 0.2 for x, and then I put in 0 for x. Well, when I put in 0 for x, the entire power series is equal to 0. Okay, so I mean, let me just see here. Let me just, yeah. Well, I mean, are there any questions on that? If I put in 0 for x, if I put in 0 for x here, every term is going to equal 0. And so that's just going to give me a big 0 here. And so now what we have to do is we recognize that, okay, this here is my series. See, I don't have a power series anymore because I have a 0.2 in for x. So now I have just a regular series, and I can use but it's an alternating series because of the -1 to the nth power. And so we can use the alternating series estimation theorem. So what we do is we evaluate, we list out the first 2 or 3 terms, and we stop when we have a term that's less than 5 over 10 to the 6th power. Because you see, we wanted correct to 5 decimal places. Okay, so that's then 5 over 10 to the 6th power. Remember, we always have a 5 on top, right? Correct to a number of decimal places. We have a 5 on top, and then 10 to the power 5 plus 1, if it's correct to 5 decimal places. And so it turns out that the second term is smaller than 5 over 10 to the 6th power. So all we're going to need to approximate this integral correct to within 5 decimal places is just the first term of the series. That's going to give you correct to 5 decimal places. So this definite integral, is approximately equal to 0.00080. So normally for these kind of problems, you know, you have to take 2 or 3 or 4 or 5 terms of the series to get the accuracy you want, sometimes even more. But for this particular problem, we only needed the first term of the series, and that gets us the accuracy we need. And it's probably, you know, if you notice this on the second terms of the series, the 0.2 to the 10th power, that gets pretty small, right? So are there any questions? All right. If we're good, I'll go to the next page then, if you're good. All right. So in summary then, by the alternating series estimation theorem, and again, we could use it because our series was an alternating series. The definite integral is approximately equal to 0.00080 or 8/10,000ths. That's correct to 5 decimal places, and in fact, it's even correct to 7 decimal places. 7 decimal places, okay, that means 5 over 10 to the 8th power. Well, that second term in the series is less than 5 over 10 to the 8th power. So you even have accuracy to 7 decimal places. That's pretty darn good. And we would have no way of knowing what this definite integral is without these Maclaurin series to help us. And these Maclaurin series can be programmed into computer algorithms to compute or estimate definite integrals. You know, you don't get the definite integral just by magic, right? There has to be some kind of, so if you're approximating a definite integral, for instance, using like something like Desmos or you know how the problems in the homework when it says approximate the integral correct to a certain number of decimal places, like if you look back in some of the problems from earlier chapters, well, how do they get that approximation? There has to be some programming involved. And this is one reason why computer science majors have to take calculus too. This kind of knowledge is important. How many think this is a pretty cool example? A pretty nice example. I mean, there's a lot there, but oh, I thought I'd have a few more hands. How many think it's an interesting example? Why don't we say interesting? We won't say cool just yet. But all right, Franklin will go with interesting. Well, Jonathan, yeah, these kind of problems, they take time to do. So how many of them are on the final exam? That all have to work out. But like this problem here, you know, in terms of points, it would be worth a lot of points on a final exam because there's a lot to do. All right, are there any questions before I stop the recording here? we're done now with section 8.7. Incidentally, section 8.7 has something called the binomial series, but that will not be covered, the binomial series. You can wait on that a little while, okay? All right, so you have now, I mean, you know, again, in example 13, the book has excellent examples. Example 13 from section 8.7, you'll want to look at that, certainly. But I think you have what you need to work on the section 8.7 assignment. So let me stop the recording here then and give you some classwork time. All right, excellent.